This view of Earth against the black void shows the current results of the Sun's steady state. For the past 4.6 billion years, this stability has allowed the biosphere to thrive. The Sun currently exists in a state of hydrostatic equilibrium, a phase of its life cycle known as the main sequence. Within the core, immense gravitational pressure fuses approximately 600 million tons of hydrogen into helium every second. This process generates the outward energy that perfectly balances the star's own gravity. This precise, invisible physics engine is the sole reason Earth remains capable of supporting life. However, the Sun's hydrogen fuel supply is finite. Every second of fusion brings the star closer to a structural shift. As hydrogen is consumed, the core slowly contracts and heats up. This pressure causes the star to burn brighter, increasing its total luminosity. A common misconception suggests Earth will remain habitable until the Sun violently exhausts its fuel billions of years from now. In reality, the inevitable increase in solar brightness has triggered a biological countdown for our planet. According to research for Phase 1, solar radiation increases approximately 10% every billion years, triggering a runaway greenhouse effect. Global temperatures rise, increasing evaporation. Water vapor traps more heat, accelerating the process until oceans boil away completely. Without water to lubricate the crust, plate tectonics will halt. Carbon dioxide builds up in the atmosphere, transforming Earth into an unlivable hothouse similar to Venus. By the 3.5 billion year mark, the Sun's luminosity will have increased by 40%. Surface temperatures will be high enough to melt rock. All life, including extremophile bacteria deep underground, will be extinguished. The end of the terrestrial biosphere occurs long before the Sun's ultimate demise. In roughly 5 billion years, the Sun will finally exhaust the hydrogen in its core. Without the outward pressure of hydrogen fusion, the core collapses under its own gravity until it is hot enough to fuse helium into carbon. Simultaneously, a shell of hydrogen outside the core ignites. This release of energy pushes the Sun's outer layers outward, causing it to swell into a red giant. As noted in the source text, its size will increase its total luminosity by a factor of thousands. This expanding atmosphere will swallow the inner planets. Mercury and Venus will be completely engulfed and vaporized. Earth faces an uncertain fate. It may be pushed into a higher orbit as the Sun loses mass, or tidal forces could drag the planet inward, leading to its complete disintegration within the turbulent stellar plasma. When the core reaches roughly 100 million Kelvin, it triggers the next stage of decline. A helium flash occurs, a runaway fusion process that converts helium into carbon and oxygen in a matter of minutes. The Sun will briefly stabilize in a horizontal branch phase, but lacks the mass to generate the gravitational pressure to fuse carbon. Entering the asymptotic giant branch phase, the star begins to convulse with violent thermal pulses, shedding massive waves of its outer plasma into space. These pulses signal that the Sun's nuclear fires are finally dying. Unable to hold on to its bloated outer layers, the Sun sheds them into the void through violent stellar winds. The remaining core becomes a white dwarf. As this table shows, it is roughly the size of Earth, but contains approximately 54. The material shed by the dying Sun forms a planetary nebula, an expanding shell of ionized gas. The conclusion of this research highlights the legacy of that ejected gas. These layers of ionized material enrich the interstellar medium, seeding the galaxy with heavy elements. The carbon, nitrogen, and oxygen forged in the Sun's core become the building blocks for future generations of stars and planets. This process of cosmic recycling ensures that the death of our star provides the materials required for new worlds to form across the universe.